So we're going to talk a little bit about some different types of tangents. So when one line is tangent to two circles, we call that a common tangent. So you can see with circle L here, right? You can see that L is tangent, or line L is tangent, to circle B and circle A. And we can also see that line M is also tangent to circle A and circle B. Remember, that is, they actually cross these different circles in just one point. Okay, they intersect them at just one point. Okay, now these lines L and M are considered common external tangents. Remember, this word external means outside, right? So what this is going to mean is that these particular tangents, eventually they're going to cross somewhere over here, right? So if we were to extend line L and line M, eventually they're going to cross right here, right? And that point of intersection is outside of those two circles, right? It's not inside, which would be right here, okay? And now, obviously, that's going to bring us to a different type of tangents, right? We can see that, similarly, line P is tangent to both circle A and circle B. And also, line Q is tangent to circle A and circle B, okay? But these lines, P and Q, are considered internal tangents because they cross, I just say inside of, right? They're going to cross right here. So we could say a couple words here. We could say they cross inside of, or better yet, I like to call this in between, right? And so again, that's why these are called internal tangents, whereas the other case that we just talked about were external tangents, okay? Make sure you take time to pause the video, write these down in your notes, okay? This is really important vocabulary to remember, okay? Now, a couple theorems that we need to remember, okay? We may see some of these on our homework here today, okay? But this says, maybe underline the hypothesis here and circle the conclusion. Okay, it says, if a line is tangent to a circle, then it is perpendicular to the radius drawn to the point of tangency. Okay, so again, this line L, it's tangent to the circle. Okay, I'm just going to kind of highlight this in red, right? Okay, this line is tangent to the circle. Okay, then it's perpendicular to the radius drawn to the point of tangency. So again, the radius drawn to the point of tangency. Again, that's going to be our conclusion here, okay? Is that, again, this line L is perpendicular to segment AB, okay? Let's go ahead and kind of scroll down and look at this other one here, okay? So this other one says, again, I'll underline the hypothesis here, okay? If a line is perpendicular to a radius of a circle at a point on the circle, then the line is tangent to the circle. Okay, and so again, let's take a look at this. Okay, if a line is perpendicular to a radius of a circle, it's showing us this right here. Okay, then we conclude that the line is tangent to the circle. Okay, that this line right here, line M, is tangent to the circle. Okay, so it's sort of working backwards than what we had before, right? And this is obviously the abbreviation that we would want to use if we're doing proofs, okay, or if we're kind of justifying our work, right? So we could just write line perpendicular to radius, or if the line is perpendicular to the radius, then the line is tangent to the circle, okay? And in this one, okay, we can kind of say this one out loud as, if a line is tangent to the circle, then the line is perpendicular to the radius, okay? And so again, those are a couple that are going to be important to remember, okay? Now, as we continue here, there's one more theorem that we want to write down in our notes that are going to be very important, okay? Again, make sure that you draw these diagrams as well. It's important that we learn these, okay? Now, this last one, okay? If two segments, okay? If two segments are tangent to a circle from the same external point, then the segments are congruent, okay? So let's take a look at this, right? It says two segments are tangent to a circle from the same external point, okay? So this external point that they're talking about, external meaning outside of the circle, this external point is A, okay? And we're saying that if these two segments are tangent to a circle, meaning that the only point of intersection here is going to be point B, and on this one, segment AC, the only point of intersection with circle P is right there, okay? Then it's saying that these two segments are congruent, okay? So again, our hypothesis here is AB and AC are tangent to circle P. Then we can conclude that these two segments are actually congruent. All right, now let's look at a couple examples here that apply this particular theorem. Okay, so this one says that segment HK and segment HG are tangent to circle F. Find the length of HG. Okay, there really shouldn't be this here. Okay, that's a mistake evidently that the book made or something like that, right? We're finding the distance between H to G. Now this point H, okay, is on the exterior of the circle, okay, and these two segments are said to be tangent to circle F, right? So again, this HG and HK, okay, are both actually tangent to circle F, okay? Now again, we can conclude that if these two segments that have the same exterior point are tangent to the circle, then these two segments are congruent, okay? So we should be able to say that segment HG is congruent to segment HK. So that would mean that the distance from H to G will equal the distance from H to K. Right, so now we're given some kind of algebra here to do. So I can just say, well, HG is 4 plus 2a. Okay, and HK is 5a minus 32. And we can just do a little algebra and solve here. I'm going to subtract 2a from each side, which will give me 3a. And I'll add 32 to each side, which will give me 36. And if I go ahead and divide each side by 3, I'll get that a equals 12. Okay? Now again, that's not the answer to my question. I just found a. Remember, we want to find the distance from H to G. So HG is going to be given by 4 plus 2 times our value of a, which is 12. And so HG will then be given by 4 plus 24, which we find that HG is in fact going to be 28. Okay, and let's look at one last example here. Okay, and then you guys can kind of go ahead and get started on your homework, or we should feel pretty confident now. Okay, so this one's saying that segment RS and segment RT are tangent to circle Q, so find RS. Okay, well R is this common endpoint that's on the outside of the circle, and it's saying that both RS and RT are both tangent to the circle, okay? Well, if these two segments are tangent to the circle and they have that common endpoint, then these two segments have to be congruent, right? So we have to be able to say that segment RS is congruent to segment RT, okay? Which is then going to tell us that these measures are going to be the same, right, by definition of congruent segments. Okay, we can then plug in the algebra that they give us. So they give us that RS is n plus 3 and RT is 2n minus 1. And then we can just solve. I'll subtract n from each side to give me this. I'll add 1 from each side to give me 4. And I find out that my value of n is 4. And so now I can go ahead and plug that into what they actually want us to find. Right? So RS will be represented by 4 plus 3. And we find that RS equals 7. Okay, so hopefully now you guys feel confident using these different theorems that we've learned today, learning about the different lines and segments that can go through on the inside or the outside of a circle.